Thanks for having me here, and I'm going to be talking about my view of the important things that are going on in deep learning in terms of what's going on inside deep learning. What are the forces that I view as the main forces driving the theoretical underpinnings of deep learning? And as mentioned, as you'll see, it's going to be highly connected to optimization. And this link between learning and optimization, I think, is hard to separate. I should say this is joint work with many collaborators. I mostly want to mention my former students and postdoc, Benem Neishabur and Surya Gunsekar, that almost all the work here is joint with at least one of them. So let's start with deep learning. And if I was giving this talk about 4 or 5 years ago, then the way I would view trying to understand deep learning is as follows. So what's deep learning? It's just we have a model class specified by an architecture. We train it on data to fit the data, and we use it to generalize. And in order to do that, we really want to, so it's just like a specific model class, a specific what I would call hypothesis class. In order to understand is it a good model class, we fundamentally have to understand 3 things. One is we have to understand what is its capacity. Okay, or in other words, what's roughly speaking, how many parameters does it have? How many training examples do we need so that if we actually fit this model, we can generalize? And actually, we do have a fairly good understanding of that. If we just look at the class of functions represented by a certain architecture, then roughly speaking, the capacity or the number of samples we need in order to generalize corresponds is roughly linear in the number of parameters. There's some details here that are not so important. The important thing is we actually have a pretty good understanding of this, and the capacity scales with the size of the network. So we need more data than number of parameters, which makes sense. The second thing we have to ask is, what can these networks capture? Right? I mean, can in fact this model class capture interesting phenomena? Okay? And so one answer to that is sort of the classic results in approximation theory using neural nets, which tell us, well, neural nets can represent everything, right? Any network, any function that's for some definition of any and some definition of approximated, any function can be approximated by a neural net. Okay? The problem is that in order to approximate a function, the size of the network has to be very, very large. Okay, so to approximate a function in RD, the number of units in a network has to grow exponentially with the dimension d. Okay? And so I really need to have huge networks to approximate functions, and that's a problem because we said that the capacity of the neural net corresponds to the number of units. Okay? And so if I can approximate it with a huge network, that doesn't do me any good. Really, the real question we should ask is what things we can approximate using a relatively small network, one that we can actually learn. And there's lots of interesting observations of that and things we can kind of learn with small networks. I mean, that have both specific things like intersection of half spaces, things that are given by small circuits, things that. And then if you ask many people about why do neural networks work well, most people definitely, if you ask, I don't want to pick on anybody specific here. If you ask the typical vision researcher using neural nets, why do neural networks work well? And they'll tell you, well, neural networks work well because really a relatively small network can capture visual phenomena very well. We have low-level features in the bottom, and then mid-level features and high-level features, and really we can capture things well. So the point they're addressing is this issue of the expressive power of the network, that it can capture phenomena we want to capture. But really, I would say from a theoretical perspective, I don't need even all these stories because neural networks can really capture everything. In what sense they can capture everything? So not in this sense. This is actually a pointer I can use, or no? Okay. Not in, that's fine. Not in this sense that I can capture any function because it's a huge network, but actually with a relatively small network, I can capture anything. It's fine. I can capture anything I'd want to capture in the following sense. So when I learn something, from my perspective, the point of learning is to, instead of actually programming something very carefully, have the computer learn for you and save you the programming. In particular, the class of things that I'd want to learn is only things that have like an efficient program to execute them, because it's not an efficient program to learn, but an efficient program to actually do the prediction. Like suppose you knew everything, you're a god, and you could create a small efficient program. If there's no small efficient program, there's no point in learning because there's just no way to solve the task anyway. And anything that I can represent, any function that for which there is an efficient program can also be represented with a neural net where the size of the neural net is roughly proportional to the size of the program, or to the runtime of the program. Okay? And so that means that really I can actually, the neural nets are universal in the sense that I actually can represent with a fairly small neural net anything pretty much that I want. Okay? So this is good news, and this really tells us that neural nets are sort of universal learners, right? That if I could actually train a neural net to fit the data, I could actually learn pretty much anything I would want to learn with a number of samples that's actually quite reasonable in the linear and the runtime. The problem with that is that in order for, so this would be excellent. The problem with that is that in order for learning to actually do learning, I also have to have a procedure for actually fitting the model to the data. And that's really where there's a problem for neural nets because we can't do that, right? So we know that if the problem of given a network, finding the setting of the weights that best fit the data is intractable. And so technically speaking, it's NP-hard. It's NP-hard even for tiny, tiny networks, pretty much the smallest network you can think of, either in 2 hidden layers. Then already the task of, even if I give you data that's exactly generated by a 2 hidden layer network, you will not be able, in the worst case, to actually find the weights that correspond to this data. Okay? And now, so this is kind of bad news, and it actually shouldn't have been too surprising because otherwise we would have been able to do this universal learning, and we know that universal learning can prove is impossible. In fact, you can also ask, well, okay, maybe exactly fitting the network is hard, but maybe it's okay because maybe if the data was generated for a small network and I fit a bigger network, maybe then it becomes easy. Okay, so that doesn't contradict the NP-hardness result. Unfortunately, there's a string of results, none of them by myself, that say in a very strong sense then that learning neural nets in the worst case is hopeless. Even if you have data that's exactly generated by a very small network, a network with, it says here I think logarithmic, you can even reduce this to a super linear number of units, okay? But with 1 hidden layer and a relatively small number of units, and you try to learn to predict it using any network or any method, okay? Then you're not going to be able to, there's no algorithm that runs in polynomial time and is guaranteed to always succeed. And this is subject to some complexity assumptions. And so really that means that the main problem when I think of neural networks, from a theoretical perspective, I can prove to you it doesn't work. Okay, I do not have an actually algorithm that can learn neural nets. But on the other hand, if I tell you neural networks don't work, you shouldn't believe me because many of you have probably trained successfully neural networks. Otherwise, if you haven't trained neural networks, you probably use things trained on neural networks. There's huge empirical success for learning with neural networks. And so what's going on here? I mean, these results are results in the worst case, right? It says that for any algorithm you give me, there exists a problem. There exists a neural net, which if I generate data from that neural net, the algorithm is not going to be able to learn it. Okay? The problems we encounter are probably not these worst case problems, right? It seems that the problems actually that we encounter in nature are ones in which very simple algorithms, just local search algorithms, actually succeed in learning them. And the big question is why, okay? So when you think of why do neural networks work, I would say that the main kind of question is not about the expressive power. Expressive power, we know neural networks have amazing expressive power, but the real mystery is why do we succeed in optimizing? And it seems that the problems we care about, kind of natural problem, visual problems, other problems for which, language problems for which neural networks have been working very well, have some kind of property. I have no idea what this property is, where this property makes it easy to train them using local search. Okay? Now the question is, what is this property? I have no idea what this property is, and I would claim that nobody has any idea what this property is. In particular, if you go to a vision researcher and they tell you, okay, why do neural networks work? And they say, neural networks work because there's low-level features and mid-level features and so on, and they capture visual phenomena very, very well. They're answering this question. And we know that this question is not sufficient. We know that having good expressive power is not sufficient in order for the training to work. Okay? So the only thing I know about this property, I don't know what this property that allows neural networks to work, but I know this property is not being able to be efficiently represented using a neural net. That I know is not sufficient. Okay? So I have no idea what this property is, but nobody else does. And the only thing I know is all these explanations of, I can have good expressive power do not provide any evidence towards why neural networks work. Is this clear? Okay. So this is where we were several years ago and really trying to understand this magic property. But this is actually not what this talk is going to be about. I just feel like it's important to talk about this before talking about neural networks. We'll get back to it later because this is, I think, really the key issue. What I'm going to be talking about is how this view, actually maybe the entire view should be changed when looking in neural networks. And this goes back to an experiment we did several years ago trying actually to answer this question. But what we found is that also all our thinking about expressive power and capacity should be changed. So what is the experiment we did? So we did the following very simple experiment. What we did is we took some standard data sets, MNIST and CFAR, and we trained them using networks with different numbers of units, different sizes. So what we see on the x-axis is the size of the network. This is not like the course of training, right? So every point on the x-axis is completely separately trained model. We took the model, we trained it just by minimizing the training error, nothing special, just gradient descent on the training error. And then we saw how well did we learn. So the black curve is the training error, how well did we fit the data. And of course, if the network is too small, we can't fit the data. Once the network becomes large enough, we can fit the data. With 64 units here on this particular data set, which is MNIST, we can perfectly fit the data. Okay. Now, the more interesting thing here is what happens to the test error. So great, so initially we fit the data better, and so the test error also improves, I have better fit. But the question is what's gonna happen past this point where I already can fit the training data better, but I'm looking at larger and larger models. So these are models that have more and more capacity. So our standard thinking says that at this point we should start overfitting. I'm not not improving fit, but I should start hurting estimation error. The model becomes harder and harder to estimate. So I should be getting a curve that looks something like this. In particular, with 1,000 units here, there's already more parameters than training examples. And so really, I mean, this curve should be even more extreme. It should just be getting nonsense. I should be able to do anything here. I'm trying to fit a model with more, using less examples, number of parameters. But when you actually run this is not what you get. And I think maybe at this point, many of you have probably seen these plots. They've been recreated also by many others. What you actually get looks like this. Okay? So what happens is that the test error actually is better for larger and larger networks. So again, so there are two phenomena that are surprising here. One is even if I just look at what happens here with 1,000 or 2,000 units, I have a model class that has much higher capacity than the number of my training examples. There's absolutely our standard explanation for the generalization ability of neural networks in terms of the capacity of the functions that can be represented by a fixed architecture completely doesn't apply here. So there's some mysterious other reason that we're actually succeeding in generalizing at all and getting small test error. The other surprising thing, maybe even more surprising, is that not only are we succeeding in fitting with these big models, but that the estimation error improves. So what does it mean? The approximation here doesn't improve. I'm not getting a better fit. The only reason that I can see a drop in test error here is because I'm getting less estimation error. The problem statistically becomes easier. Why does the problem become statistically easier even though the model class is larger? That doesn't make any sense. Okay, so that suggests that the way I'm measuring size of my model class in terms of number of parameters is wrong. Okay, I should be measuring it some other way. Okay, so this phenomena is actually not new, and some of you might, the plots like this might look familiar. In the late 90s, people were kind of in the same place in terms of understanding boosting. So also for boosting is a proper algorithm, and it was explained the initial learning guarantees for boosting were in terms of the number of base classifiers used, roughly captured by number of rounds. And so based on the standard analysis of boosting, then if I already have zero training error, if I add more and more base classifiers, the number of rounds increases, I should see an increase in the test error. But people actually saw a decrease in the test error. And then in the 90s, people scratched their head trying to figure out what's going on until Bartlett, Freund, Lee, and Schapper provided a different explanation and said, well, really, actually, the correct complexity measure here is not the number of base classifiers, but rather the L1 norm of the predictor captured by the L1 margin. And what they showed, this is just a plot taken from their paper, is that what happens between using 5 base classifiers and using 100 base classifiers is not that the training error decreases, but what decreases is the margin. I'm getting a much better L1 margin. And that's, there's a margin explanation of boosting, which is basically boils down to a different complexity measure. And it turns out that around the same time, when Peter Bartlett studied this for boosting, there is also, and this is a mostly ignored paper. It appeared in some workshop, Australian workshop and something, I don't remember, in 97, talking also about neural nets and saying that also for neural nets, for generalization, the size of the weights, some measure of their magnitude, is more important than the number of the weights. Okay. So now that we have much more empirical experience with neural nets, we can ask, well, can we explain the phenomena we had before using a similar explanation that we had here? That maybe what's happening is during the course of training, it's not that even though I'm using larger and larger number of units, then their magnitude is maybe smaller. So my model class effectively is smaller because I have smaller magnitude units. So we can check that. So this is the same plot I had before. I'm just focusing here only in the regime in which I already have zero training error and trying to explain why does the test error decrease. And if we try to mimic the same type of thinking, then what we should plot is plot the norm of the weights. And maybe we can see that even though the size of the number of the weights increase, their norm decreases. So let's plot the norm of the weights here. And what we get is the norm of the weights look like this. Okay, so this actually doesn't explain what's going on because if the norm decreased, we could say, oh, the effective model class is smaller because it has smaller norm, but actually the effective model, the norm here also increases. Okay, so now the question you should be asking me, which Julia just asked me, is what norm am I plotting here? This is not the L1 norm. What I plotted here is the overall L2 norm of the weights, the sum of the squares of all the weights in the system. Now, there are many other norms I can plot. I can also plot the L1 norm. I actually get a very similar plot. I can plot all other kinds of crazy norms. Okay? So now it's a question of choosing the right norm. And if I at least plot this norm, which is the path norm, so this is a norm. So the problem here with all these norms is that they treat the weights as abstract numbers that have nothing to do with the actual computation that's going on in the network. Okay? So this is the path norm. The details of this norm is not so important. It's the sum of all the computation paths in the network of the products of the weights along the path. Yeah, I can define some norm. And if I plot with this norm, then I do actually see a phenomena that more matches what I'd expect. That at least in terms of this norm, then indeed when I have larger networks, even though the number of weights is maybe larger, their magnitude as measured by this norm is smaller, and that might explain why I generalize better, because my effective model class is smaller. Okay, but now the questions we should ask is, first of all, what is this norm? And it need not necessarily be a norm. What is this relevant complexity measure? I mean, I came up here with some norm. This is not the right answer. I mean, this is just, it looks nice, but there are many reasons that we know this is not the right answer. If we think that there's a different complexity measure here that's actually capturing the capacity, not the number of units, but some other complexity measure, what is this complexity measure? Okay? But there's even a more basic question. So if I look again at these networks with 1,000 hidden units, okay? So the solution that gradient descent found has fairly small path norm and very good test error, very small test error. But this is not the only solution. So a solution here is something with zero error. So we found a solution with zero error, with zero training error. But there are many other solutions with zero training error. So all of these other red dots here also correspond to solution with zero training error. All of these are global optima of my objective function. Okay, so my objective function here was just minimize the training error. All of these red dots are global minima. I know they're global minima because there's zero error. Okay? And many of them generalize horribly. Many of them have horrible test error. Okay? And indeed, we can see that the ones that have horrible test error, at least among the ones I plotted, are ones with high path norm, and the one that has small path norm has low test error. So that's consistent with saying that the path norm, or some other maybe norm, some other scale measure, really captures the capacity here, that if I limit myself to things with small path norm, I'll be able to generalize well. But I didn't ask the algorithm to minimize the path norm. All I told the algorithm was minimize the training error. Why is it that the, sorry. That's, I have to work hard for that. It's not easy. So I had to, I intentionally, so the question is a very good question, is that how did I construct these bad global minima? Okay? How did I construct these global minima on the upper right? It's actually very difficult to construct them because if I use any reasonable optimization algorithm, I'm not going to find them. So I did something very unreasonable. I mean, inside my optimization algorithm, I worked hard in order to maximize the test error. Okay? I cheated and looked at it when I optimized. So you gave me the training set, and I will actually optimize the training error. But I'm going to cheat. I'm going to peek at the test error and work hard to increase the test error. and return to you a solution that in fact does minimize the training error, but also does as bad as I can on the test error, on the test set. Okay, so it's a legitimate global minima of the training error. Okay. Not quite as bad, but it performed bad. Okay. Okay. The point is, it doesn't matter how I did it. The point is that there exist other global minima that are bad. Okay. Okay. So again, the question is, why does my optimization algorithm, that all it was told was to minimize the training error, why does it actually find the solution that actually has small path norm? Why not these other solutions that has high path norm or high, that are more complex? Okay. So, and again, in terms of the optimization, I refer to these as bad global minima. They're not bad in terms of optimization. So if you're an optimizer and I give you this problem, minimize the training error on this training set, and you return to me either any of those points in the upper right, you did your job perfectly well. These global minima are legitimate global minima, and they have, they minimize your optimization objective. They're bad I'm being unfair calling them bad because they're bad in terms of a criteria which I never specified to you, I never told you about. Okay, so how is it that your optimization algorithm actually minimizes? So the first question is, what is this criteria? And the second question is, well, how come your optimization algorithm minimizes this criteria? In particular, that suggests that if I change my optimization algorithm, I'm going to change my criteria that I'm implicitly minimizing. And if I change my criteria that I'm implicitly minimizing, and we said that all the generalization properties actually comes not from the size, but from this complexity measure, I change my complexity measure, I'm going to get different generalization properties. And in fact, we can see this empirically, and you see this empirically all the time. These are some examples I have here. So what we did is we changed, instead of using standard gradient descent or stochastic gradient descent is steepest descent with respect to Euclidean norm, and what we did is approximate steepest descent with respect to this path norm that we saw before. It doesn't really matter. The point is that we have two optimization algorithms, the red algorithm and the blue algorithm. Both optimization algorithms, if I look at the left plot is the training objective. Both of them are perfectly fine in terms of the training objective. They both find the global optima of the training objective. The blue one may be a bit faster than the red. I don't care about that. Okay? But if I go to the right plot, this is the test error, we see that the blue algorithm is finding a much better global minima. Again, what I mean by better, it's not better in terms of the objective. It's the same in terms of the objective, but it has some other it's better in terms of some other unspecified property. Okay? And we see this across the board. Here's another example comparing SGD and atom. So atom, you don't need to know what atom is. I mean, it's a variant of SGD that includes momentum and some adaptation of step size. It doesn't matter. There's a blue algorithm here and a red algorithm. Both of these algorithms are doing a decent job at optimizing the training error. Okay, you don't see it here, but trust me, if you continue this long enough, they're both going to get to the same training error. Okay? The red algorithm actually is a bit better in terms of optimization. It gets there a bit faster. But now when I look at their generalization properties, the red algorithm is actually much worse in terms of the tester, in terms of generalization. So the blue algorithm somehow finds a better global minima. Okay, and again, better in a way that I didn't specify. Okay? So my claim here is that all the inductive bias, all the complexity measure, everything that allows me to generalize is coming just from this implicit bias introduced by the optimization algorithm, right? Because without it, I'm going to be in this situation where on the top right there, where I can get arbitrarily high test error. Okay, so if is there a question? Yeah. So I'm considering yes. The short answer is yes. So right now, think of an optimization algorithm as including also the initialization. Okay, I didn't specify in these how I initialize. On Thursday, I'm going to be giving another talk. All of it is or much of it is going to be about initialization and the effect of initialization. Okay. Okay. So where were we? Okay. So what we're saying is that all the inductive bias, all the complexity measure is specified only by the optimization algorithm. That means that when we think of suggesting a generic neural network algorithm, usually we focus a lot on the model. We specify the model. Okay, so we talk about our architecture and how our architecture is great and it can capture a lot of things. But really, I would say all this is not important because our architectures usually are big enough; they can capture everything. Okay, they're close enough to being in the situation that we talked about at the beginning that they can approximate essentially any function. In particular, they can definitely fit any data. Okay? And then we say once we have this model class, then we kind of brush off the optimization. Oh, we just minimize the training, fit the model by minimizing training error on the minimizing the training error on the architecture. And how we do it, it's not so important. And I would claim that how we do it is the whole important thing is how we do it, because all my actual learning rule, my actual inductive bias, my actual choice of effective model, the complexity measure actually specifies the effective model, is captured inside here in terms of how do we actually optimize this problem. So roughly you should think about it this way. So I'm optimizing here. The problems in deep learning, we usually deal with highly underdetermined problems, highly overparameterized. I have many, many more parameters than training objectives. In fact, and we'll get that later, maybe you should think about optimizing over the space of full functions. Maybe that is the correct view, actually, if going back to these classic approximation theory results. And so if I look at my loss landscape, think of this as my loss landscape, then I have many, many global minima. Okay, in fact, I have tons of global minima. You should think of those global minima. They're all at value 0. You should think of them as the oceans, right? So I have tons of oceans that are at level 0. Okay, and I start optimizing. I start optimizing, on some top of some hill. And now the question is, which global minima will I get to? Well, I'm not going to get to a global minima in the middle of the ocean, right? Because I'm going to do local search, and I'm going to find. I'm going to stop when I get to a beach. So I'm going to stop. I'm going to get to a beach. The question is, which beach? Okay, which beach am I going to get to? So, okay. Paris is not a good location for this, so let's switch back to America. If I start optimizing in Boston and I go down, then I'm going to get probably to the Atlantic Ocean. I start optimizing in San Francisco and I go down, I'm probably going to get to the Pacific Ocean. The question is what happens when I start optimizing in Chicago. So Chicago is even flatter than Paris. Paris at least has some hills. I know it's, Chicago is completely flat. From Chicago, the river in Chicago flows backwards. I know, I'm serious about this. The Chicago River actually goes backwards. It's so flat, okay? So you can get from Chicago just by going down. You can get either to the Gulf of Mexico or up to the St. Lawrence Bay or, with some effort to the Atlantic. You can get to lots of different places. And the question is, which directions do you prefer going? Or what is the geometry of your local search? If your local search is a geometry such that it prefers going south, you're going to get to the Gulf of Mexico. If it's a geometry that prefers going north, you're going to get to the St. Lawrence. Okay? And which global minima you're going to get to, which of these are you going to prefer, is highly tied to the geometry of your local search. Okay? Okay, and the thing is that in high dimensions, it's much, much, much worse. Because in high dimensions, really, you can go down and get to lots of different places. Okay, so the geometry of the local search really determines where you're going to get to. So what I'm going to do in the remaining I have half an hour or so, is try to, so this was pretty abstract. I know some of you are maybe like nodding and saying, okay, I understand what I'm getting at. Some of you are looking at me and like, this doesn't make any sense. So what we're going to see is some concrete examples. So what we're trying to do now is trying to understand this phenomena. And we'll try to understand this phenomena by looking maybe at simplified models and seeing how everything I told you about how the geometry of the local search really determines all the generalization properties of the algorithm comes up in several simplified models. So the first model we're going to look at is the maybe only model that I have some understanding of. I've been working in it since my PhD thesis, and this is matrix completion. Okay, so we're going to solve a matrix completion problem. So we have a partially observed matrix, and we want to complete the unobserved entries. So we're going to write this as just a least square problem of minimizing. We're going to solve this by having an unknown matrix X, and I want to fit the observed entries. So I'm going to minimize the error between the observed entries in X and their actual observations. And I'm going to optimize over all matrices X. Okay? So this doesn't make any sense whatsoever, right? Because I'm not constraining here X in any way. I'm not biasing in any way. The problem is completely underdetermined. It's underdetermined in a completely useless way. I mean, there's lots of global minima here. In particular, I can copy the observed entries and put zeros everywhere else. I'm going to get a global minima. Or I can copy the observed sequences and put the Fibonacci sequence everywhere else, or write 73 everywhere else. All of these are perfectly valid global minima. Okay? And all of them are also kind of useless. Okay? But nevertheless, this is the problem we're going to solve. Okay. But the way we're going to solve this is, so if you could solve this and do gradient descent on X, and that's actually not going to get you anywhere. You do gradient descent on X, you're only going to touch the observed entries. That's a very kind of lazy approach to training, and you're not going to generalize at all. So what we're going to do is as follows. We're going to do exactly what you do when you train deep networks. You only have an undetermined overparameterized model. We're going to overparameterize it even more. So instead of having here, you have d squared parameters with much less observations, and instead we're going to have 2 d squared parameters. So I'm going to parameterize X as u times v, where u and v are full dimensional, right? So if X is d by d, u is d by d, and v is d by d. So now the problem is even more ridiculous. Okay? It's even more parameters, and it makes even less sense. Okay? This is exactly what we do in deep learning. Okay? So in particular, this is, if you squint in the right way, this is a two-layer network with linear transfer. Okay? But okay, for now, we can just think of matrix factorization. And this is a problem we're going to solve. And again, this is just as stupid a problem as before. I can still get any matrix X I can represent as U times V, so I still have all the same global minima. I can write U, one solution is writing U equals the observed entries with 0 completed, and V equals the identity. Okay? There's a perfectly valid global minima, very easy to find. Okay? Nevertheless, we're going to take the stupid problem that doesn't make any sense, and we're going to do what we do in deep learning, which is solve a problem that doesn't make any sense using the simplest possible algorithm, which is gradient descent on U and V. And the question is, what happens when I actually optimize it using gradient descent on U and V? Okay, so let's see. And so what I'm going to look at, so what you get is as follows. So first of all, I actually did here both gradient descent on X and gradient descent on U and V. So for comparison, so both if I do gradient descent on X and gradient descent on U and V, first of all, I get 0 training error. Okay, big deal. It's very easy to get 0 training error. I mean, I found a solution that completed the observed entries. The more interesting thing is if I look at the test error. So this is the error on the unobserved entries. Okay, actually, the way I measure it here is measure the error on all the entries. Okay, so if I look at gradient descent on X, the error on all the entries is useless. I mean, the only reason it's not 1, it's 0.7 is because it's on all the entries, not just on the 30% of the entries were observed. I get completely useless error on the unobserved entries. But if I do gradient descent on U and V, then actually I get pretty good test error. I mean, I get, like something above 10%. It's not bad. I actually succeeded in generalizing pretty well, even though there's absolutely no reason I should have. I mean, the problem itself doesn't make any sense. But now let's change the optimization algorithm a bit. Instead of what I did here is gradient descent with exact line search. And instead, I'm going to do gradient descent with a fixed small line search. Okay? So again, this is a worse optimization algorithm. It's a worse optimization algorithm because, I mean, both of them are going to find the global minima, but it's going to, this worse algorithm with using a fixed small step size is going to take much longer. And line search is great if I can implement it. But actually, this worse optimization algorithm actually generalizes better. Now I'm getting a test error of about 5%. Okay? So what's going on here? Can I explain why is it that when I solve this completely underdetermined, nonsensical problem using gradient descent, I actually generalize well? Okay, so in this case, I kind of understand what's going on. So it turns out that by doing gradient descent on U and V, at least if I use small enough step size, so infinitesimal step size, and going back to the question about initialization, initialize infinitesimally close to 0, then what I'm actually finding is not just any global minimum, so any solution that agrees with observation, but among the solutions that have 0 error, I'm going to find the minimum nuclear norm solution that agrees with observations. Question?
Just to make sure,
yeah.
The train error is on the entries you observe?
Yes. So actually in this plot, maybe I should change them. Here, the training errors, no errors are observed. What I'm measuring here is what says relative error. It's actually the error on the entire matrix, both the ones I observed and the ones I didn't observe. Okay? But it's just, does this answer the question? Yeah. Okay. Okay. So I see this empirically. I mean, in fact, the nuclear norm, the rightmost column here is actually the minimum nuclear norm solution. And what I see is that I get actually the same nuclear norm as the minimum nuclear norm solution. And now I can kind of understand all the parts here. I know what the complexity measure that's actually going on. It's a nuclear norm. I didn't specify it, right? The problem specification did not include the nuclear norm. Okay? So I uncovered the complexity measure. I also see how am I getting small nuclear norm solution. Doing gradient descent and factorization implicitly biases me towards solutions with minimum nuclear norm. So I understand that part. And now I also understand why nuclear norm is good for generalization. That I knew already from before. Many of you probably know that at least if I have, if my data is, say, approximately low rank, then minimizing the nuclear norm actually gives good generalization properties. And in fact, the way I generate the data here is approximately low rank data. Now note that this is not cheating because I generated the data that's approximately low rank, but the model didn't know this, right? The model optimized over all matrices. Okay? And so now it kind of completes the whole story. And now I have to rethink back about what is the correct notion of the expressive power here. Okay? Why is it the model works? It's not because I can represent my data using my model. I can represent anything using my model of U times V. It's because I'm actually implicitly looking for a low nuclear norm. So what I should ask is what things can I actually represent with small nuclear norm? In particular, things that are approximately low rank I can represent with small nuclear norm. And I should think of the capacity, not the capacity of all matrices, but the capacity of matrices with small nuclear norm. Putting all these things together completes the picture here and tells me exactly what I'm finding. Now, I should say that this statement is a bit rough. When I tell you that you get a minimum nuclear norm, I only know to prove it in certain cases. So formally, okay, I'm going to go through this very quickly. If somebody's interested, I can point you to the relevant papers. If you look at this problem a bit more generally, not just for matrix completion, but with any linear measurements of unobserved metrics, then the conjecture is that without any assumptions about how the data, where the data comes from, if the initialization goes to 0 and you do gradient flow, so gradient descent of infinitesimal sizes, you'll get to the minimum nuclear norm solution. We know how to prove this only for the special case where these observation matrices A commute with each other. That's definitely not the case for matrix completion. Okay? The conjecture is that it holds more generally, and if somebody wants to look at it, I mean, our justification is empirical and with in terms of some hand waving. What happens if the matrices don't commute? Then you have some time-ordered exponential here that you have to argue about what happens at the limit and kind of wave your hands a lot and say, well, at the limit it looks like it commutes even though it doesn't commute. I have no idea how to make these arguments rigorous. If somebody wants to look at this, I'd be thrilled. There's also other authors showed this in other special cases. So our analysis doesn't use any statistical properties. If the data actually does come, if the measurements are incoherent and the underlying metrics are incoherent, so if the data actually is reconstructible, then again, Tengyou Ma and his students proved that you actually again get the minimum nuclear norm solution. And I should mention that we don't even know if this conjecture is exactly true. Empirically, there's some small numerical discrepancies. I actually think these small numerical discrepancies are because the initialization has to be extremely small in order to get exactly the nuclear norm. But it's not clear if maybe there should be some correction. Even if there's some correction, it's still the broad picture. You get, at the very least, you get something which is almost a minimum nuclear norm, which also is very surprising. I mean, why would you get that? So this is the situation here. Okay, so let's go back and so we already saw an example. Of how all the story I told you before happens for a specific problem of matrix completion using the matrix factorization. But now what we really want to do is kind of build a dictionary that connects the optimization algorithm, the implicit complexity measure that actually, and the implicit complexity that actually minimizes. Okay? Yes?
Just one question about the flow. So the initial point of the trajectory must be 0?
Well, it can't be 0 because 0 is a saddle point. So the statement, the conjecture is as written here. You look at, so as the initialization, you look at the solution as a function of the initialization. As the initialization goes to 0, the endpoint of the trajectory goes to the minimum nuclear solution. Does that answer? I can get arbitrary close. Right, and in this work, for this specific case, well, no, they didn't exactly make it quantitative. They sort of made it quantitative in terms of like how close to 0 they have to be in order to be close to the minimum nuclear norm. Okay. So what we're trying to do is build a dictionary relating the optimization algorithm and what solution you get to. So we started with what I would consider the simplest possible example, which is just least square problems. Okay, and so for least square problems, indeed, it's very easy to see that if I have an underdetermined least square problem and I optimize it with gradient descent, I will actually get the minimum nuclear norm, minimum Euclidean norm solution. So the base case is very easy. And now we try to generalize it. So in fact, what we saw now is we look at the gradient descent over factorization. And we already ran into trouble because we saw that this is actually very delicate. We could uncover the complexity measure, which is a nuclear norm, but we only got it with infinitesimal step size and infinitesimal initialization, whereas the result for just gradient descent on a least square problem is with any step size. And we couldn't exactly prove it. It was like already a miss. Okay? We also tried other things. So I mentioned in the beginning Adagrad. And we asked, can I characterize if I solve a least square problems with Adagrad? What do I get? Okay? Any guesses? For those who know Adagrad? I'm curious, how many people here are familiar with Adagrad? Okay, some people. Okay, so I mean, if you are familiar with Adagrad, a good guess would be that you're minimizing the L infinity, finding a solution with minimum infinity norm. And it does happen in some very special cases, but actually doesn't happen in general. In fact, we can prove that it's not possible to characterize the solution a grad will converge to. It depends on what happens inside the algorithm. It depends on the data. We also looked at just what happens if I change my local geometry explicitly. So gradient descent is steepest descent with respect to the Euclidean norm. If I do steepest descent with respect to some other norm, okay, what happens? So instead of taking each time trying to making the best, infinitesimally the best progress by taking a small Euclidean norm step, if I try to make the best progress by taking some other norm step. So I kind of expect that I'd find the solution that minimizes that corresponding norm, but that's actually not what happens here. It turns out to be much messy, and again, you can specify it. And it turns out we actually kind of knew it because for those of you who are familiar with Lars, Lars is essentially steepest descent with respect to the L1 norm, and we know that that's related to the lasso, which is explicitly minimizing the L1 norm, but it's not exactly the same. So it seems that actually least square problems turns out to be harder to analyze than we expected. Fortunately, that's not actually the loss functions that used in many deep learning. The loss function that's typically used in deep learning is what's now being called the cross entropy on the softmax, or in other words, logistic regression. So just logistic loss. So let's analyze logistic loss. So let's go back to the linear model and just look at the standard logistic regression problem. So it's a neural net, right? Neural net with a single, I should use the modern vocabulary. This is not logistic regression. I'm fitting a neural net with a single unit, okay? With cross entropy on the softmax. So logistic regression. And now I have a training set, and of course the question is interesting when the problem is underdetermined, right? So I have tons of ways of separating the data. The data is linearly separable, and there are many different ways of separating the data. And I optimize it with gradient descent. And the question is, where will gradient descent converge to? Where would the weight vector of gradient descent converge to? Answer to the audience? What? Well, so first of all, it's a trick question. Why is it a trick question? So the weights vector will actually not converge; it will diverge. Okay. So the only way to drive the logistic loss to 0 is to drive the weights to infinity. So the weight vector will actually diverge. Okay, will go to infinity. But that's fine. I mean, really what we care about is not the weight vector, but just the direction. Okay, so I mean, I'm going to have the weight goes to infinity, but it's going to go in infinity in some direction. It's going to define a separator. So the real question, the real question we're asking is in which direction will it go to infinity? Will it go in this direction to infinity, defining this separator, or in this direction, defining what I'm seeing here is not what I'm seeing there. That's fine. Or in this direction, going to infinity. Can we study the direction which will go to infinity? Okay, that will define me what separator I converge to. Okay, so now I'll again ask for guesses. Which linear separator I converge to? What would be your first guess? Okay, the max margin. Of course, so we go to the max margin. So what we get is the max margin solution, or the hard margin SVM solution. Now again, I did not specify neither margin or hinge loss or L2 or anything in the problem. Any of these directions which I go to infinity is a valid way of approaching the global minima, or the global infimum. Okay, there's no global minima here. But if I choose to optimize logistic regression gradient descent, I can prove to you that I always converge to the max margin solution. And this is independent of the initialization. So now to answer your question, initialization does not matter. It'll happen for any initialization and for any reasonable step size. I mean, as long as the step size is not ridiculously large. Okay, let me skip this part. Okay, and now we can ask the same questions we asked before about what happens if we change the optimization algorithm or change the setup. So if we do now steepest descent with respect to some norm, then now in fact we will get max margin with respect to that norm, right? So we get do a steepest coordinate descent, steepest descent with respect to L1, we'll get max L1 margin. You do steepest descent with respect to your favorite other norm, no matter what norm, what you'll be doing is getting large margin with respect to that norm. Okay? So that's good. We already get a vocabulary. And also, if you go back to the metrics factorization problem, then now we can again reconstruct the same result, but now it's much more robust. It's independent of initialization, and we can actually prove it. Okay, so things here are much simpler. And the situation, and the reason that things are simpler is in some sense the asymptotics here are nicer. So for the squared loss, and it's not because of the squared loss specifically, I mean, any loss that looks roughly like this, then the minimizer is finite. which means that I'm going to go to a finite point. And so the effects of what happens early on in optimization give me a finite effect. In order to wash them away, I have to start taking all kinds of limits, taking the step size to 0, taking the initialization to 0. If I look at logistic regression, this divergence is actually what helps me. I'm going to go to infinity anyway. Since I'm going to go to infinity, who cares what happens close to the origin? Okay? So it makes all the analysis much easier and the results much more robust. Okay, so now that we're starting to understand neural nets, we already understood a neural net with a single unit. Let's try to understand what happens with neural nets with more units. But we'll still talk about linear neural nets. Okay? So a neural net with a single unit, I converge to the max margin, to the hard margin SVM. What happens if I have a linear neural net? So what's a linear neural net? Linear neural net, now I have a bunch of units. Each unit implements a linear function of its inputs, and the transfers are all linear. So at the end of the day, this linear neural net just implements some linear predictor. It's just a complicated way of parameterizing a linear predictor. So you could tell me, well, why am I doing this? I'm just linear predictors. Why am I parameterizing this way? But you already saw before, then changing the parameterization, parameterizing x as u times v changed a lot, right? So it does make sense to look at what happens in different parameterizations. Okay, so this is just a parameterization of a predictor. And so I can ask again, what is if I train a fully connected linear neural net with gradient descent, which predictor am I going to converge to? I'm going to converge to a linear predictor. Which linear predictor? And it turns out the answer is actually pretty boring. No matter what the architecture is, I'm still always going to converge to the max margin predictor. Okay, no matter how many layers to max L2 margin predictor, standard hard margin SVM solution. No matter how many layers I have and what's the width, it doesn't matter what, I'm still going to get the same boring solution. But what happens when I look at linear conv nets, linear convolutional nets? Okay? So what's a linear convolutional net? So I'm going to look at full width linear convolutional network. So now, if I have d inputs, then at each layer I have d units, and each unit has d weights. All the units, though, share the same weights. They're just shifted by 1. Right? So each unit implements a linear transformation, a linear function on the layer before it with weights that are shifted by 1 relative to the unit next to it. Okay? So what I get is a convolution. Each layer is a convolution of the previous layer with some arbitrary set of weights. Okay? And again, so this is so the two differences here versus more conventional convolution networks. Well, okay, three. One is I'm looking at the 1D case. That doesn't matter. That's just because I cannot draw things beyond 1D on the board. The other thing is that I'm looking here at full width convolution, not kind of with a small number of taps. And the third is, of course, this is still a linear convolutional network. So in particular, since it's a linear convolutional network, what I can implement is still just linear predictors. So at the end of the day, I'm just going to get a linear predictor. Again, this is just a strange overparameterization of linear predictors. And I can ask the same question now. If I train this convolutional neural net with gradient descent, which predictor am I going to converge to? I'm going to converge to a linear predictor, but which linear predictor? Any guesses? Somebody that has not seen this talk before? Guesses? Which linear predictor I converge to? So it's going to be a max margin, but not max margin with respect to the L2 norm. It's going to be, max margin with respect to L2 norm means I'm kind of implicitly finding a solution with small L2 norm. Here I'm going to be finding some other solution with some other norm. Any guesses? Okay. No? Okay. So with one hidden layer, I'm going to converge to a max margin, or I'm going to converge to a solution minimizing the L1 norm in the frequency domain, the L1 norm on the Fourier transform of the predictor. Right? So I'm looking at the predictor as a set of weights. I'm minimizing its Fourier transform. So I'm getting something that's sparse in the frequency domain. But more than that, if I have multiple layers, we said that for a fully connected network, it doesn't matter how many layers I have. Here, it is going to matter. If I have multiple layers, if I have depth L, then I'm going to be implicitly minimizing the bridge penalty, the LP bridge penalty for P is 2 over L in the frequency domain. So again, so if I have 10 layers, then I'm going to be minimizing the 0.2 quasi norm in the frequency domain. So I'm going to get something that's very sparse in the frequency domain. Okay? So it looks something like this. This is simulated data. Training a fully connected network. What I'm showing you is the actual weights that I get. The red is I didn't even remember which one. One of the colors is blue is the empirical and red is the theoretical prediction. So if I get a fully connected network and train it, I get some predictor that looks like the top thing there. Once I have a convolutional network, I already get something that looks pretty sparse in the frequency domain. And with 5 hidden layers, I get like super sparsely in the frequency domain. So again, I introduced here very meaningful inductive bias. Okay, so that I understand. I know that if I'm using a linear convenet and optimizing gradient descent, I can characterize what is this complexity measure, what is the inductive bias I'm introducing. It's some kind of sparsity and frequency domain. And now I can ask, is this inductive bias good for me? Does it give me good expressive power? Does it allow generalization? Okay, okay. So what we saw in these two examples, in looking at matrix factorization and in linear convenets, in both cases, I didn't actually change the optimization algorithm. The optimization algorithm was, well, or I didn't mess around. The optimization algorithm was very benign. It was just gradient descent. But rather, what we did is we changed the parameterization. And by changing the parameterization, we got very rich inductive bias. In particular, in both cases, the model class was everything. Okay? So a different type of everything. For matrix completion, it was everything in the sense of all matrices, right? That's my everything here. So I had the model class of everything. And the only thing I did is I parameterized everything in an interesting way. I parameterized everything as a matrix factorization. And now when that imposed some geometry on the way my local search on the space of everything on the space of matrices was such that I still did local search on the space of matrices, but it's such that I got to the minimum nuclear norm solution. Okay? Because by changing the parameterization, I changed my geometry of the search. Similarly, for linear convenets, everything here was all linear predictors, right? The problem is just linear, so everything, we're just talking about linear predictors. I still looked at all linear predictors, but all linear predictors here is too much because the whole point is the problem is underdetermined. I mean, there are many more dimensions than data points, okay? But again, by choosing this strange parameterization, okay, it's not that the standard view maybe is that the choice of architecture determines my model class. Here, the choice of architecture, it's not that it determines my model class, but rather the choice of architecture, this convenet, it still gave me everything, but it determined the way I explore this model class. It imposed a specific geometry, local geometry on this model class. And when I did local search under this geometry, namely by doing gradient descent on the weights of the convolutional layers, then it imposed this very rich inductive bias, which is sparsity in the frequency domain. Okay, so in both of these examples, the everything was either all matrices or all linear functions. We also can see this really talking about all functions. So for that, consider fitting a function, univariate functions, from function from R to R. So we're using a single hidden layer ReLU network. So with a large enough single hidden layer network, we know that we can approximate any function, again, for appropriate notion of any. Okay? And in fact, we are going to look at large enough. We're going to look at infinite width network. So with an infinite width network, so I have an infinite number of units, I can really capture any function from R to R. But now the question is, what happens when I actually fit the data using this network? So I'm going to perfectly fit the data because I can actually look at every function, but what inductive bias do I get? And here I should say that at least to get this result probably holds even without it, the formal result does rely on weight decay. And any guesses? So again, the question here is I look at the space of all univariate functions, all functions. I parameterize them using an infinite width ReLU network. And now I fit the data by doing gradient descent with weight decay on the weights of this ReLU network. And I'm asking which of the many functions that fit the data will I actually get? Okay, so I'm going to be implicitly minimizing some complexity measure. Here, the complexity measure with nuclear norm. Here, the complexity measure was this bridge penalty in the frequency domain. What would be the complexity measures and functions here? Okay, so the answer is the complexity measure turns out to be roughly the second order total variation. So the integral of the absolute value of the second derivative of the function. Okay, so again, I did not specify this explicitly. This is just specified implicitly in terms of the geometry imposed by this choice of architecture. Okay? And nevertheless, it's a very sensible complexity measure. Okay? So it's some measure of smoothness, and I can get generalization guarantees relative to it, and I can now say that I can now tell you which univariate functions can I learn with the infinite width ReLU network. Well, it's those functions for which the second order total variation is reasonably small. Okay? We're working now in so this is still this is still for univariate functions. The point is, again, it's another example that we have everything. Our model class doesn't, the architecture does not specify the model, or the architecture does not limit the model class. The model class is everything, all univariate functions. What it does is just imposes geometry inside that. So basically the picture we're getting is something like this. We're doing the optimization in the space of weights, but what we really care about is the space of functions. Okay? And probably the correct thing to look at it really is that, going back to that very first slide, is the classic approximation theory result. We can represent any function using a large enough network. And the networks we're using are actually large enough. Okay? And I would argue that really this is the correct way to think about things. Okay? And now, where does the geometry come in? Roughly speaking, inside the weight space, I have a fairly simple benign optimization algorithm, just gradient descent, that imposes a relatively simple geometry. I don't know, something. It's actually kind of difficult to say what it is when I have nonlinear models, but it's a relatively simple inductive bias. But since what I care about is not what happens in parameter space, I care about what happens in function space, this mapping from parameter space to function space turns this relatively benign, simple inductive bias to very rich inductive biases in function space. Okay? Things like nuclear norm, like sparsity in frequency domain, like second order total variations. So by the choice of a good choice of parameterization, a good choice of architecture, what it does again is it's not that it limits my model class, but it gives me a very rich geometry in the model class that implicitly defines some complexity measure that allows to generalize. Okay, it should be wrapping up, right? Okay. Okay. So maybe I'll skip this then. Okay. So this is. So now let's revise our view of deep learning. Then, really, what this means is that what we should be. So we still should be thinking about this magic property, because how come this optimization actually works is also a big question. But that means really we should be thinking differently about both expressive power and capacity. The expressive power here now is not what can I represent with neural nets, okay? But rather we have to think about what is this inductive bias inside the set of neural nets, and then what can we represent where this complexity measure is small. Okay? And in terms of capacity, what we should be thinking about is not the capacity of the sets of functions represented by a neural net, but the capacity subject to these complexity measures. And we do have, I didn't talk about it here, but both from my group and other groups, there is a lot of work recently on understanding these questions of generalization. And finally, what I talked about a lot today is when I think about optimization, I should now think about two questions. Both these questions of why does optimization succeed, but also the question of not succeed, what succeed? Finding a global minima by itself is not enough. The real question here is what does the optimization imply about the type of solutions they find? Okay, and this is maybe the most interesting question to me about the link between optimization and learning in a deep network and what we're working on now. Okay, so I'll end here, and I'll just say that I'm going to be giving another. Is this okay to say it here? I don't know what the. No? Okay. I'm going to be speaking also on Thursday at an undisclosed time and location, in which it'd be a much more technical talk, actually focusing in part on these issues of initialization and on reconciling some of the view here about the rich implicit regularization with other recent results that taken at face value suggest that all we're doing here is just using a big kernel. So that's I'm going to be talking about on Thursday. Thank you.
Thank you, Nati. Any questions? So sorry, maybe you said it at some point, but in the case the functional that you are minimizing is non-convex, like when you have more than two layers, if I understood correctly, what does it mean to minimize it? Is it like finding global minimizer, or is it like? So
let's separate to two things. So the problem here, I should have maybe emphasized it more. The problems here are non-convex. All the problems I described are non-convex. So even going to the metrics case, right? The problem in terms of x is convex, right? So minimizing the error of the observed entries on x is a convex problem. Once I go to UV, not only do I increase the number of parameters, but I also made it non-convex. So it really seems like completely stupid. In all the other linear models are also, anything that's more than one layer is non-convex. So there are two separate questions. One is, will I find a global minima? And the second, if I find a global minima, what will the global minima look like? The one way to take the results I showed here, and some of them are also phrased this way, is they're all conditioned on finding a global minima. So in particular, the results in the linear conv nets say that if you converge to a global minima, this will be the global minima you'll converge to. However, in many of these problems, it's relatively easy to prove that you will actually converge to a global minima. So both for, in particular for matrix factorization and for fully connected networks, it's relatively easy, fully connected linear networks, it's a different question, it's relatively easy to prove, sometimes under mild assumptions, that you will converge to a global minima. Okay? I believe that's the case also for convnets, but we didn't bother kind of doing that. And so usually I think these questions can be answered separately. And today I kind of focus on the first part, and again, whether you convert to global minima is also definitely relevant. The other thing, which I don't think is what you asked, but maybe, so some of the implicit regularizers I mentioned are also non-convex. So in particular, the bridge penalty in the frequency domain is non-convex. So I can't actually minimize the bridge penalty in the frequency domain. And so even though I told you I'm minimizing it, I think I had it correct on the slide. What I can guarantee is just that the global optima, what I'm going to converge to is going to be a solution with, if I can, okay, the formal statement here is that, okay, so it says here, if I actually get loss goes to zero, if the loss goes to zero, then I'm going to get to a solution that's a stationary point for this non-convex implicit objective. Okay, is that, I don't know if that was what was bothering you, but yeah. Okay.
Question? So the path norm that you described at the beginning is something. You say it's not correct, but it's something that we should think is rather good, and why, or no?
It's
just
rather
an example.
good. Okay, so good for what? It seems to be good in the sense that, for example, it captures. It's a better norm on the weights, and in particular, as I showed, doing steepest ascending with respect to it instead of steepest ascending with respect to the Euclidean norm does seem to be better. You mostly see that for regular neural nets, the difference is not very big. Or you see a big difference is actually for recurrent neural nets, where it's just the recurrent neural nets end up being very, very big, and they're hard to optimize, and using this helps. It's not the correct. The reason I said it's not the correct complexity measure that captures what's going on is because to be the correct complexity measure, sublevel sets. What I kind of want to find, what I would argue is the correct complexity measure is a complexity measure such that sublevel sets of that complexity measure have bounded capacity independent of the number of weights, or almost independent. Okay, and that's not the case not true for the path norm. The sublevels. I know what the capacity of the sublevel sets of the path norm. We can work it out, but it does have a polynomial dependence on the number of units, and so that's why it's not actually correct in explaining what's going on.
All right, I have one last question. Sure. So if I want to find the max margin solution, should I run the hinge loss with L2 penalty, or should I just do a logistic run?
Okay, probably you should just run the hinge loss with L2 penalty. But okay, so let me answer. Give two answers. Or three answers. One, you should just run L2 with just run L2 hinge loss with L2 penalty. The second is that if you actually run gradient descendant logistic regression, okay, so the reason you shouldn't just run L2 in logistic regression, this is actually, okay, that's actually an important point, so I skipped this, I think. So even though I actually maximize the margin, it turns out that if I can ask how fast do I maximize the margin, and where is it here? And it turns out that I'm maximizing the margin very slowly. So what is going on here? This is like got a life of its own. Okay, so I am, the margin goes down only as, in terms of number of iterations, as 1 over log t. So even though I'm getting the max margin solution, I'm getting there extremely slowly. So that means it's a very bad way of maximizing the margin. And that's actually an important point. If you go back to, this might explain what's going on if any of you have trained a neural net. I'm curious actually, how many people here actually trained a neural net? Like looked at the numbers as they go down? Okay, quite a few. Okay, so when you train a neural net, what you frequently see is that when your training error improves from 1.6 times 10 to the negative 7 to 1.3 times 10 to the negative 7, then you actually get improvement in test performance. This doesn't make any sense because the improvement you're getting in test performance is not 10 to the negative 7. It's like 10 to the negative 2 maybe. Okay? And so why is it that such tiny changes in the test loss actually translate to significant differences in tiny differences in the training loss translate to significant differences in generalization performance? what might be happening here is, as we said, even though doing gradient descent and logistic regression actually maximizes the margin, it does so extremely slowly. And so to get the really close to the max margin, you really need the test loss to be 10 to the negative 20. And so when your test loss goes down from 10 to the negative 7 to 10 to the negative 8, what's really going on is that you're working on that margin. Okay? And you're actually seeing maybe a significant improvement in the margin, which is why maybe you're seeing improvement in training error. And we see this, okay, I'm not going to go through this, but you see this empirically. There's empirical evidence for this on real networks, not just logistic regression. So for this reason, it's a bad idea. I mean, if you just want the max margin, just do the max margin. I should say that you can partially solve this by playing with the step size. So we do have work that if you do normalized gradient descent in a specific scheme, you can actually get to be almost as fast as doing just hinge loss plus L2, but you're still not going to be better than hinge plus L2. So now, I know this is not the question you asked, but I do feel I should answer this. Why, if it's such a bad way of maximizing the margin, why should I do this? And so the point here is also, you can ask this about the metrics factorization. Why do this stupid thing? Why just not minimize the nuclear norm directly? I mean, that also works great. So what we're trying to see here is look at what actually happens. The objective here is to understand why is training deep network actually working. So when I'm training a deep network, I know what algorithm. I'm fixing the algorithm you're using. You're using gradient descent on the training error. That's what you're doing. Okay? And I want to understand why that works. Because then maybe we can improve it. Okay? Maybe we can tell you, oh, use some implicit regularizer or use something else. It's not to say, if you know already what is the regularizer you want to use, then just use it directly. Don't come up with a strange optimization algorithm that implicitly would give it. Okay, yeah.
But then maybe you will maybe you will discuss more this on Thursday. So somehow also the initial condition is very important, right? Because it means that if you start from initial condition, which has a very high value of the norm, then, I mean, dynamically, except if you run for a very long time and maybe it will depend on the loss, you will not get to the good solution. Right. So there are both things, initial condition and, of course, the algorithm.
So I consider initial condition as part of the optimization algorithm. Right? I mean, the optimization algorithm is specified as, give me a training set and I'll optimize it, right? So choosing the initial condition is part of that. But yeah, definitely the initial condition. So as I mentioned here, things like initial condition, step size, these things can make a huge difference. And we have some understanding of that, and I'll talk more about on Thursday about the importance of mostly of the initial condition and maybe also step size.